Hello, everybody. Good morning. We are starting this second webinar of RE4 Project. I see that there are some attendees still joining us, so we will wait a little. Okay, we wait for just 1 minute for some attendees, and then we will start. Thank you. Hello, everyone. We are starting this second webinar of RE4. I'm Serena, and there's Paolo here with me.
Good morning, everyone.
We are from ACR Plus, and we will support Phoenix during the moderation of this webinar. So just some issue about this platform that we are using, GoToWebinar. During the webinar, you will be able to ask any question you want, or even during the presentation of the panelists. We are going to have quite a lot of panelists today. So please, when you have a question that you want to ask, just go in, just type it and send it to us, and we will receive it. You just go to question, and you can type there the question. If you have any problem, just go to chat menu, and you can type there, choosing Secretariat ACR Plus, and like you cannot hear us or you cannot see the slides, or you don't know how to send the question, you cannot find it, just send a message there, and we will reply to you. Right now, I will give the floor to Susanna from Phoenix, and she will introduce the webinar and the panelists. So thank you, everybody, for joining us, and enjoy this webinar.
Good morning, ladies and gentlemen. I'm very glad to welcome you to the webinar of the European Research Project RE4. This is the second webinar in the series of 4, and you can watch the recording of the previous webinar on the RE4 website. My name is Zuzana Tatyakova, and I'm representing Phoenix TNT, dissemination and exploitation leader of the project. Today we have 6 presentations on the topic of RE4 prefabricated building elements, incorporating up to 100% of construction demolition waste. Now I would like to welcome our first speaker, Alessandro Largo. He is the project coordinator, and he is the head of the Resilient and Sustainable Civil Engineering Unit in CHETMA. Alessandro will present the RE4 project to you. Alessandro, the floor is yours.
Well, good morning, ladies and gentlemen, and thank you very much for attending this session related to prefabricated building elements with construction demolition waste. And thanks a lot also to Susanna for the introduction. As said, today I will introduce you the RE4 project, a European funded project of circular economy in construction. Before I get to the heart of my presentation, I would like to briefly present CHETMA. It is an Italian RTO founded in 1994 and located in Brindisi in South Italy, with skills on materials engineering, industrial design, and ICT. Our industrial priorities are materials and construction, transport, productive systems, energy, and healthcare. Coming back to the RE4 project, it is a project of circular economy for the construction industry, which is according to the last available key figures from the European Construction Industry Federation, one of the main drivers of the EU economy, accounting for more or less 9% of the European gross domestic product, with 10 billions of euros of turnover and 6.5 of total employment. However, construction industry is also responsible for the main waste streams at the European level, which is construction demolition waste, which account for more or less 800 tons per year. The interesting point is that quite a lot of those construction demolition waste can be recycled in high-grade application, but they are very often confined to low-grade application or landfilled. Moreover, there are other materials from construction demolition waste, which are wood, plastics, and glass, with a very high recycling potential that is, however, unexploited so far. That's why in this scenario, Europe has set the challenge of the development of energy-efficient building concept using new or adapted prefabricated components, allowing the reuse and the recycling of different materials and structure while reducing energy use and minimizing environmental impacts. And Europe also set the targets of a minimum share of recycled materials in the final product of at least 10 to 15%. And this challenge was taken up by the RE4 project, which has developed a fully prefabricated, energy-efficient, easy dismountable and reusable building made of concrete and timber components containing up to 65% by weight of CDW-derived material and structures. And to reach this goal, we gathered a multidisciplinary consortium coordinated by CETMA and made of 13 partners from 7 different countries across Europe and 1 non-EU country, comprising 5 among university and research centers, 7 industrial partners, and 1 association. The project has an overall budget of about 5 million euros, and it started in September 2016, and it will end in February 2020. While moving on the RE4 concept, there are 4 main pillars supporting the project. The first 2 are technical and refer to the maximization of CDW recycling and reuse. In terms of recycling, RE4 has developed advanced CDW sorting technologies to improve the overall quality of the CDW-derived products, as one of the main constraints for growth is the quality, which is not always good enough when compared to virgin materials. And at the same time, RE4 has also fully exploited the recycled potential of lightweight fraction from construction demolition waste, which is currently unexploited. This process has been supported by the compliance assessment of each sorted fraction against relevant national and European specifications, with the definition of new quality classes for CDW-derived aggregates, with the aim to support the development of new standards in the fields of construction demolition waste. As final, the recycling potential has been verified with the development of a set of RE4 materials and prefabricated elements incorporating high ratios of construction demolition derived materials. And the RE4 aimed also to improve the state-of-the-art recycling rate from 80% to 95% and to improve resource efficiency in terms of virgin material replacement of at least 65%. In terms of reuse, RE4 has developed new sustainable strategies for the disassembly and reuse of concrete and timber structures and building components that reached the end of their service life. And moreover, the project has developed innovative design concept for a fully prefabricated, easy dismountable RE4 building with up to 90% of reusable structures. The concept has been designed in such a way that multiple applications for different building typology, for example, residential or commercial, will be easy to implement. And the RE4 elements have been designed to be tailored to different climatic as well as structural requirements of different geographic zones across Europe and outside the EU. Well, these are the goals from a technical point of view. However, we know that this is not enough to push the EU to the forefront in the area of the CDW management, but also other non-technical barriers have to be tackled as well. And the first one is related to the overall management of the CDW value chain. That's why by tackling the CDW management at different level, RE4 aims at contributing to reach the targets of recovery and recycling by 2020. This is built upon a proper stakeholder engagement since the beginning of the proposal preparation and upon the development of a BIM-compatible DSS tool to support owners and construction demolition company by providing an estimation of the type and quantities of CDW that will be generating during construction demolition, with also possible utilization option and related logistic references. This new approach to the CDW management will also generate new attractive business opportunities as well as new technical skills, like for example, CDW managers. The second one is related to the end user acceptance, as it is well known that people do not want to hear about materials from waste. And that's why RE4 proposes many activities to increase end user acceptance in the use of secondary raw materials. And this is based upon LCA, LCC, and social LCA analysis, HSE analysis, performance assessment, certification, and standardization strategies. Finally, training videos will be provided for all of the most relevant activities of the project and will be used for students and new technical profiles. Well, let's now see a brief overview of the main results obtained so far by the project, and to each results we have devoted specific presentation both today or in the forthcoming webinar sessions. So it is possible to build a fully recycled house. The RE4 project answered yes. Nevertheless, it is crucial to adopt a circular approach and to address all the main steps of the construction process. That's why the RE4 project has developed solutions in terms of design for reusable buildings, the construction strategies, CDW sorting, CDW quality assessment, development of material and prefabricated components incorporating high ratio of CDW, digital tool to support all the actors of the CDW management. All of the RE4 solutions have been demonstrated and validated in real environment in 4 RE4 demo buildings. And here you can see in the right picture the Spanish RE4 demo building, a 2-story building made of prefabricated concrete and timber components, fully reusable with a replacement rate of virgin materials in the range of 50 to 85%. In terms of figures, the RE4 project has developed a set of statistics, both lesson learned and recommendation in terms of CDW management, 4 new technologies in terms of deconstruction, sorting, design, and digital management, 6 new solutions at the material level in terms of new quality classes for CDW derived aggregates, and 5 new materials incorporating on average the 78% of CDW, 8 new components, both structural and non-structural, incorporating on average 82% of CDW, and 4 demo buildings, 2 for new construction and 2 for renovation. We have also tried, and we are trying to share as much as possible these results, as we know that the transition from a linear to a circular economy in construction has to be promoted at all the levels of the CDW management value chain. And moving to the RE4 impact, the European Commission set the goal of a CO2 saving by 30%, energy saving by 20%, and a minimum share of recycled materials in the final product of at least 10 to 15%. And on the right graph, you can see the RE4 results. We gained a CO2 saving more than 50% on average, energy saving of more than 45% on average, and a share of recycled materials in the final product of more than 50% on average. Moreover, RE4 solution resulted also to be cheaper than conventional solution of more than 15%. To conclude, the RE4 project has demonstrated how CDW derived materials extraction can be effectively reintroduced in the production cycles of concrete and timber components with a replacement rate in the range of 50 to 85%. Moreover, from a technical point of view, a fully prefabricated 100% reusable building is now a reality. Well, the way is paved, but there is still a strong need of improved waste identification, separation and collection at source, quality assessment procedures, and mainly policy and framework conditions that can foster the transition to a circular economy in construction. Well, thank you very much, and I'll be happy to reply to any question during the question time.
Thank you very much, Alessandro. Our next presenter is Ruben Correa. Ruben has been coordinating large consortium research and development projects for CREAH Concrete. He also works as structural engineer on CREAH's Ireland residential division. And recently he designed and detailed the new concrete laboratory facilities for the company as part of the RE4 project using CREAH's concrete precast system. Ruben will present the RE4 structural elements. Let us welcome Ruben and his presentation.
Thank you, Susanna. It's a pleasure to be part of this webinar. I have to say hi to everyone listening. My name is Ruben Correa, and I have been coordinating CREAH Concrete efforts in the RE4 project. CREAH Concrete, let me present the company beforehand. CREAH Concrete is a large precast company established in the UK and produces all kinds of construction precast products, from concrete blocks to large sandwich panels. Okay, coming back to my presentation, I just want to show with this presentation the challenges, developments, and achievements in the production of the RE4 structural elements. Just bear with me because this presentation is a bit long and there's so many areas that I want to discuss. So I may tend to be fast in certain slides. So if there's any questions or you'd like me to explain better something, please mention at the end during the Q&A time. So what were the challenges on this project? First, the development of materials from CDW in quantities enough to produce the structural elements. Second objective of the project was to assess the CDW quality and find ways to guarantee the consistency of the raw materials supplied during the entire manufacturing process. The third objective in the RE4 for the structural elements was to develop the precast elements and integrating high levels of CDW materials into them. Also combining a fast assembly, a fast construction, and also developing elements that could be easily disassembled. Finally, we had to demonstrate the RE4 structural elements at the industrial scale, and all elements were produced here at CREAH facilities. Yeah. Moving on to the development of materials, incorporating high levels of CDW. All structural elements are made of reinforced concrete. So the focus of the materials went to the concrete development. This was already discussed, and here I just want to show you the mixes used at industrial scale. These mixes contain CDW aggregates, cement, limestone fillers. We had to, on the structural elements, we developed we used three mixes. One self-compacting concrete, another one a semi-dry concrete and vibrated concrete. The vibrated concrete was to be used into the stairs manufacturing. So what were the major challenges when using CDW aggregates? One of the biggest challenges in the concrete manufacturing is related with the consistency of supply of raw materials. Contamination can be another problem, and quality insurance. That is, if the materials supplied or received are specified by the initial criteria we have. So after careful analysis and based on CREA experience dealing with aggregates from different sources, a method for receiving, storing, and handling the CDW aggregates was done in the project. The main procedures for this are to store to source the aggregates in bulk. This guarantees less variability of the aggregates. All deliveries should be inspected to ensure they meet acceptance criteria. This inspection includes also the inspection for contaminants. Because we store the materials in stockpiles, these stockpiles need to be turned and mixed prior to concrete production to avoid segregation. We can store the aggregates under cover to avoid high levels of moisture. The moisture is tested daily during the manufacturing process. So if it's too high and you cannot use the aggregates, they are placed under cover so they can dry and be used into the concrete manufacturing. Also, this aggregates are tested. We perform sieve analysis for each batch of material received, and to make sure that the aggregates meet the supplier specification. Another thing that from experience we know when dealing with difficult sands and with we saw that with the CDW aggregates is that the aggregates can segregate and stack into the bins when we are at the batching plants before going into the concrete manufacturing. So we only use vibrated bins to place the aggregates at the batching plant. Now, moving on to the development of the structural prefabricated elements. So I just want to take some time to talk about the design, because many times this is neglected, but a lot of effort went to design the structural elements during the RE4 project. So we come up after a long and extended period of discussions with all partners. We come up with two structural systems. One frame precast system based on columns and beams, which involves a more typical system for seismic regions. This system uses a non-load bearing sandwich panel on the perimeter and is fixed to the frame structure. This building can be completely dismantled and reusable. So we made sure to develop good connections here for the elements, and to use good connections to easy construction and easy disassembly of the elements. This precast system is adequate for new multi-story buildings. Another system which is based on CREA experience and CREA rapid rest system is a panelized precast system, which uses wall panels, has main load-bearing elements. We have from CREA experience and other projects, we developed load-bearing sandwich panels, which are used in the perimeter of the buildings with cross walls to complete the structure. It's the cheapest system and use a reduced number of elements, and so there are less lifts on site. This type of construction is also adequate for multi-story buildings. This will be discussed a bit more detail in the next webinar when we're going to talk about the demo buildings. But basically, we had developed a frame precast system to show in the demo building in Spain, and the panelized precast system is being shown here in the UK. And at the time I'll talk more about the types of connections used in both the demos. The frame precast system uses bolted connections. These connections were off-the-shelf products, and we worked with especially one supplier, Payco, and they have bolted connections for wall-to-wall connections, columns to columns, and columns to beams, and so on. Regarding the panelized precast system, it's a different connection system, and uses mainly to connect wall panels to wall panels, a wire loop connection with a rebar going through the loops, and which is grouted. It's a shear key, as you can see in the pictures on the right. And this system also uses blocks, pipes inside the wall panels, where the rebar can be placed and do a continuous joint, and will link the whole precast elements together. I just want to talk a bit more about the sandwich panels, because they are the main components taken from the RE4 project. These sandwich panels are cast in two layers. One is a structural layer, and can take as a load-bearing layer. Then we have isolation layer and a face layer. This face layer is the facade, so you can have different finishes from bricks to a concrete exposed finish, painted finish, so you name it. The structural layer usually is 150 millimeters thick. The isolation can vary depending on the project to project. On the RE4, we used 100 mil isolation layer, and the face of the panel, the outside of the panel, is composed by a 80 mil layer. I know that Linus, after this presentation, will discuss the non-load bearing sandwich panels, which are similar to these ones. Also, I want to discuss in terms of the design is the detailed production drawings. This drawings many times are neglected in terms of the efforts, but many times was dedicated to producing the drawings for production, where we specified and ourselves together with Xiona and ITC and CR universities in Naples. We took a lot of time to detail each element, structural element in the RE4 product. You can see there in the pictures, there's on the left a rebar drawing from a sandwich panel. You can see all the rebar that goes into a panel like this, rebar schedules, everything there's a lot of detail on those drawings, and on the right, mold drawings for a column that was shipped to Spain. We try to use as possible 3D modeling, so the guys in the factories know what they're doing, so they can see, especially when come to this requirements of the RE4, where we have a lot of specific different connections, and they have to be placed spot on. They cannot fail the positioning. So in total, we produce a lot of elements, structural RC wall panels, 6 beams, 3 columns, 5 solid floor slabs, 49 hollow core reinforced concrete slabs, 16 load-bearing sandwich panels, and 4 stairs. These are only the structural RE4 elements produced. More non-structural elements were produced as well. I just want to show you a bit of the CREA facilities in Tunbridge, Northern Ireland. We have in total 12 individual factories. Actually, we are building another one, and next year we're going to have 14 individual factories where we can produce all kinds of concrete products. And we produce the RE4 elements mentioned before. We have steel fixing factories where we can make bespoke concrete elements, stairs factories where all the RE4 concrete elements were produced here and shipped to Spain and Italy as necessary. The main production line has 120 meters long and comprises of 12 tilting and vibrating heated steel beds. You can see there in the picture on the left, and here on the bottom as well on the left, you can see one of the tilting tables. They are made of steel, and the surface is very smooth, so we get the best possible finish from the concrete we are laying into it. On the right, you can see at the bottom you can see the stairs factory opposed to the normal tables. They are inclined at an angle, so the stairs can be at the right position. They can be adjusted, but they are heated as well. So stepping on to the production process, we can divide the standard reinforcement concrete elements production into 6 main steps. So where we have firstly the steel reinforcement, then the mold preparations with timber and plywood, and which is fixed to the steel molds shown before. And then we have the concrete manufacturing process. All the concretes are done here on site at different batching plants. Then once we have the concrete, we can pour the molds in the factories, and then once the molds are cast, there's a curing stage and a finishing stage where the elements are left to cure and to the concrete to gain enough strength so it can be demolded and lifted. And there you have REC element produced. Now I'm going to go in more detail to each step and to show you the pictures of the manufacturing process. So first we start with the steel preparation. Steel bars and steel meshes are cut, bent, and welded to form the shape specified in the drawings and by the notes of the structural engineers. Actually, we form a steel cage with the shape of the element and this cage is delivered to the factory where the panels are being cast, and they are ready to be placed and fixed to the mold. You can see there in the pictures some of the cages we produced in the RE4 project. Starting from the left to right, we have beams with the beam shoe at the end, the connection for those beams. We also have in the middle one of the wall panels that we produced to the Spanish demo site, where you can see a connection at the bottom of the panel, and the reinforcement required for this panel, and on the right the reinforcement for the structural layer of a sandwich panel with all the lifters and so on. The second step is the mold preparation in the factories. Most of the precast panels are bespoke products, and individual molds are prepared for different designs. The base of the mold is a heated tilting vibrating steel table, as I mentioned before. This base can be referred as the panel's face, and is usually taken the surface of the element that requires the best possible finish. It's usually taken as the exposed face. And each mold is prepared by setting the wooden shutters and against the steel base to form work with the shape of the element. The mold is cleaned from debris, and release oil is applied, and the reinforcement is set up with appropriate copper spaces. All features placed, lifters, connections we can fix, M&E pipes, and so on. You can see there on the pictures there some of the molds prepared. On the left we have molds for wall panels. On the right on top we have the molds prepared for the stairs, cast against the ramps in the stair factory. Beams and columns on the right, and more wall panels with the reinforcement already placed into the molds. And other details, just for you to see the kind of craftsmanship that is required for making the RE4 elements, where we can see on the left the column shoes fixed to the mold before ready to be cast, several beams with all the grouting pipes and connections required. The stair mold ready with the steel reinforcement ready to be placed, and on the right at the bottom you can see a wall panel from the RE4 project with all the connections and steel reinforcement in place and ready to receive the concrete. So as mentioned, the next step is the concrete pouring. All concretes are produced at on-site automated batching plant. This batching plant, the quantities are controlled by a computer and measured automatically after the concrete mix design is introduced into the computer. Then the concrete is transported to the factory using a truck, a lorry, as they call it in the UK. At arrival at the factory, a sample is taken, and the slump flow test is performed. If as from this sample also is taken for later compressive strength testing. If the slump or flow is approved, the concrete is discharged into a 2 cubic meter skip, which is used to pour the concrete into the molds. There's vibration and the tilting tables if it's required for it. Usually it is not, because we have to use for the horizontal panels and columns and beams, we use the self-compacting mix developed during the RE4 project, and we're happy with that. So we didn't use vibration at all when casting these elements. As you can see in the pictures, the concrete is very flowable. When casting sandwich panels, because they have 2 layers of concrete with a installation board in between, there's extra steps in the production process, which I'm going to show here and in the next slide. So when after casting the outer layer of the sandwich panel, then we have to place the installation boards ready after with the fresh concrete in place, so we can the connecting pins that will link both layers can be placed into the fresh concrete of the outer face. Then once we have all the installation placed and the pins all fixed, the rebar and features of the structural layer can be fixed to the mold. I'm sure you can see there the pins that connect and the 3D image of how the pins connect both layers of concrete. The outer layer, which represents the facade of the element, and the structural layer inside. And at the bottom, you can see pictures of how it looks like when manufacturing these panels, and some detail on the right, some details of the positioning of the lifters and connections. Then the second layer of the sandwich panels are cast in some similar way as I explained before. We get the concrete from the batching plant and using the skip, the structural layer is poured. After all the casting of the concrete elements, and as soon as the concrete begins to harden and the consistency of the surface is adequate, these elements are manually or mechanically rolled depending on the level of finish required. The panels then are left to cure in the factories on the heated tables for approximately 16 hours before the next stage. The bed, we try to keep the bed at 20 to 25 degrees, which we found that's the most accurate temperature to cure the concrete and achieve the requirement of 15 megapascals for lifting. You can see there are some pictures of the guys finishing the wall panels and sandwich panels on site, and on the right you can see one of the beams already cast in the mold. Okay, the next stage of the production process is molding and lifting. When the concrete reaches 15 megapascals, we can lift the panels. The strength of concrete is tested by testing two cube specimens, and if the strength is above 15 megapascals, then the panel or the element is molded, lifted, and transported to adjacent area.
Ruben, I'm sorry for interrupting, but we are running out of time, and I would like to ask you to, in 2 minutes.
All right, okay. I'll try to step out. Okay. So next stage is final finish and quality checking, where all the panels are checked for any defects and applied any finishings if required. Now I just want to discuss a bit of try to speed up discuss a little bit of the home span, which are hollow core RC slabs, and were produced using semi-dry mix developed during the RE4 project. This factory is it's fully automatically, and we produce this as a standard product. And you can see there we have steel molds, and the rebar is placed similarly to what we've seen before. And there's steel pipes that slide along the molds that form the hollow sections. Then the casting is done by a fully automated batching plant inside the factory. It's the only one we have here on site. And there's an automated discharge system that pours the concrete directly into the mold. This mold vibrates and then automatically turns and demolds the fresh slab into a rack. This is only possible using a semi-dry mix. Then, as similar to the other elements, the slabs are lifted and placed in an area to cure. Once they are cured after normally 2 days, they are pushed into a conveying system to be stored outside. The slabs before being stored are inspected, then lifted and stored until they are ready to go to site. All the industrial demonstration was done during the drive, because we focused on the concrete in such a way because we were confident if the concrete worked, because these are only reinforced concrete elements. If the concrete worked, we know that the structural elements would work. So we developed the structural elements and tested the structural elements at the industrial scale. Here I just want to show a bit of the quality testing, and we performed here. We follow very strict quality testing of the concrete, and here we can see a table with the mixes of the RE4 and how they perform. They perform very well, and everyone and the production team was very happy with the concretes developed during the project. All the concretes achieved the required strength and the workability we anticipated and we wanted at industrial level. During the production, as I said, everything went smoothly, just small issues and some details of the connections, but that was adjusted as required, and no non-conformities were noted during the manufacturing process. We just noticed some brownish stains on some of the panels, probably due to the high content of clay in the sands or the aggregates. And finally, we have the final products of the RE4, which were used in the demo sites. We have wall panels, solid slabs, hollow core slabs, columns, and beams. All elements were produced here at CREA. I just want to say that the RE4 elements are comparable to standard concrete precast products, and here at CREA we were very happy with this project, and we are using the elements for our new concrete lab, which is being installed as we speak. And here we can see sandwich panels, big sandwich panels, 8 tons. Some of the panels were manufactured using the RE4 technology, columns and beams, and a wall panel that was sent to Spain. They are hanging on the crane. I just want to thank you, and I'll leave you my contact details if somebody has any questions or want to be in touch. Thank you very much.
Thank you very much, Ruben. Our next presentation will focus on RE4 non-structural sandwich panels and will be presented by Linus Brander. Linus is leader of Work Package 5, which is dealing with the development of materials, components, and elements. Linus is a research scientist and project leader at RISE, Research Institutes of Sweden, and works with applications for aggregates, dimension stone, concrete, and secondary raw materials. Now let's hear about the non-structural sandwich panels from Linus.
Good morning, everyone. So, good morning, everyone. Thank you, Serena, for that introduction. The non-structural concrete panel that we have worked with together with CREAG. Here you actually see a photo of the structural panel, but it's very similar in view. The non-structural concrete panel that is actually a sandwich element with CDW-based concrete inner and outer layers. So CDW stands for construction demolition waste, and a conventional insulation. And one different from the structural elements that Ruben told you about is that in this particular panel, the outer layer consists of high performance concrete, which is textile reinforced instead of steel reinforced. I will show you a little bit more about that later. When producing these concretes, we have a span of replacement level of CDW, which runs from 50 to 80% for the self-compacted concrete and 50 to 20% for the high performance concrete. The reasons for this span, it will be evident for you later. And finally, these elements have actually been casted by CREAG and tested and included in demo buildings. You can really say that's successful upscaling. So, but going back to the beginning, traditionally you use aggregate, as you see here. In this case, primary aggregate. You mix it with cement and water, some admixtures, some additives maybe, and you have a concrete, and you make concrete products of it. But in this case, we skip the primary aggregate and instead use this. Ruben has already told you about it. This is how it looks like. So this is CDW provided by our partner CDE and Environmental. And you can see it's a little bit primary concrete aggregates. It contains bricks, ceramics, clinker, but also crushed concrete and unbound stone. So, but usually we, as you see here, we don't fully replace the aggregated CDW. Usually we have a range, so that's why this primary aggregate still peeps up behind it here. So, I'm going to a rough layout of a conventional panel. This is how it looks, a little bit simplified, with inner and outer layer surrounding in insulation, and having a conventional self-compacting concrete, which is steel reinforced, just like Ruben showed in these nice photos from the CREAG factory. But what we have done also for this, in this case, for the non-structural panel, is that we have, like I said, used CDW-based self-compacting concrete, and instead of a 80 millimeter thick conventional concrete layer, we have reduced the thickness by half and instead use high performance concrete and carbon textile reinforcement, which is actually one layer. Sorry for that, it's wrong in this image. So, and to say something about how you actually achieve this, because this is of course the end, what we have achieved in upscaling, but it has of course been some work to get there. We started actually on industrial scale by the partner I mentioned, CDE, who provided the CDW Then, of course, it's some work in the laboratory where you need to characterize and quality assess the CDW using it as concrete aggregate. Then you, of course, need to adjust your mix design for your concrete mixes to with replacement of CDW. And in our case, we have also, before going to upscaling to CREAG, we also wanted to test different textile reinforcements to be in the outer layer to decide which type of reinforcement to go for. So this is actually what I'm going to focus on in my presentation, the laboratory work in between these industrial scale works. So starting with the concrete, I will not mention so much from aggregate characterization and assessment, because that will also be an issue of a later webinar. So, but after your characterization, you have your CDW, you know how its properties compared to virgin materials, and we use this line of work to adopt and optimize mixes, both for self-compacting concrete and for high-performance concrete, starting with screening tests on small batches, like 15 liters, to look at workability and short time properties, like compressive strength after 1 day and 7 days. As Ruben mentioned, they need, for example, some early strength development in order to demold and work with the elements as soon as possible after casting. And in this way, we can vary a lot of different properties, like the primary aggregates, replacement level of CDW, different cement content, and so on, in a relatively short time to really optimize, get as high as possible CDW replacement and still fulfill the industrial partner requirements. Because, of course, as Ruben mentioned, CREAG Concrete, in order to use this, they need, they have, of course, properties they want to be fulfilled. So, and after screening test, identifying some candidates, you could go for a more full-scale test program on larger batches and also a lot of other properties and also durability properties. So as an example, to the right, you see the requirements from CREAG on the final strength class of the concrete, the slump flow of the fresh concrete, and it should keep this workability up to 30 minutes after mixing, and also this strength development. As Ruben mentioned, after 16 hours, they need 15 megapascal in order to demold and lift the elements. So here we show two different, in the screening test, two different mix designs and their properties in terms of slump flow, workability, and also compressive strength the first week. The previous was actually, there was a few examples of self-compacting concrete. We also ran this screening tests for high-performance concrete mixes. And here you actually see it's the same properties that CREAG wants to, that this mix should achieve. But here you also see something happening, depending on the CDW source, the one we call SE. In that one, we succeeded to replace 90% of the aggregates and fulfilling the properties CREAG requested. When changing to another CDW, which we shortened UK, we only succeeded to replace 50% and fulfilling the requirements. And the reasons for this is that these two different CDWs, they have different quality. Just shortly, this will be an issue for a later webinar, but shortly, the quality class of concrete is of CDW as used in concrete is stipulated in this EN standard for concrete, EN 206, with two different classes, A and B, where A is the better one, and the more concrete and unbound stone you have, the higher the quality, and with more bricks and tiles and bituminous material, that generally lowers quality. So looking at these two different batches, SE and UK, that we used with the present system, EN 206, the SE batch is a B class, and the UK don't even qualify, and this is reflected in actually in the amount we can replace. So it's interesting. It's good when it's actually, this is logic that we could turn it around. With this quite not so good quality, we still managed to replace 50% of the aggregate and still keeping the required requirements of CREAG. So the next step for us, when we had developed self-compacting concrete and a high-performance concrete that we were satisfied with, was that before upscaling at CREAG, we wanted to test which type of textile reinforcement to use in the outer panel. So therefore, we set up a test scheme with where we produced test specimens using much smaller molds than they did at CREAG for flexural strength test, and also pull-out strength for these anchors, these pin connectors. And we used two different textile reinforcement, alkali-resistant glass fiber and carbon fiber. And with carbon fiber, we tested with 1 or 2 layers. I shouldn't say too much about it. In total, we tested 42 specimens. Here you see the how it looks like. This is 4-point flexural strength, also measuring the displacement. The pull-out test. Here you actually you test how much strength you need to pull out a connector, and then you assess the damage done. I will not say too much about this, other than that from these 42 test specimens and these 2 tests conducted, our conclusion was that we should go for 40mm thick outer layer as shown previously, and 1 layer carbon textile reinforcement. So this is actually what we could provide to CREAG for their upscaling. Ruben has already shown pictures from the upscaling work, and the first step in the upscaling was that they used the mixes that we developed, and they made some adjustments. But the interesting thing was that even though they used another type of cement, another type of primary aggregate, other fillers, other admixtures, the only thing they needed to adjust was to adjust the amount and type of superplasticizer a bit. They used the same CDW because CDE delivered CDW from same batch to us and to CREAG. So this was really interesting. So this is actually the 3 large elements from the first upscaling for test elements, and this is part of the crew at RISE who has helped me, or to be honest, they have done the work. I just sit there. With these elements in 4-point bending strength, once again to confirm that that was the right choice to use 1 layer carbon fiber in the outer layer, because one of these 3 panels were 2 layers carbon fiber in the outer layer. And the results from this 4-point bending strength test surveyed by digital image correlation was actually that 1 layer proved to be the best one. So to conclude, before going to upscaling, there's some need of adjustments. But if you have done a good work in a structural way to investigate how different changes of material affects your concrete mix, it don't need to be so big to replace virgin aggregates or primary aggregates with secondary ones like these recycled CDW. The challenge with these aggregates is typically the water absorption that is a bit higher than what at least we are used to in Sweden, where we have often very low water absorption values. But that can actually be, if assessed in the right way, for example, by pre-saturation or surveying, okay, how much water does this contain, and then calculate with it when you proportionate your concrete and count how much water you need. It doesn't need to be such a big issue. We also noticed that actually when using a CDW of a little bit lower quality, we had to reduce our ambitions on replacement. And that is also interesting that it's actually confirmed. This is a confirmation of this quality assessment system. We also noticed, except in this first upscaling in industrial environment, we noticed that it's quite different it's quite hard to work with textile reinforcement, because you pour large batches of concrete on these small nets. So, and particularly with 2 layers, it was a bit hard to keep them in place. So the choice to go for 1 layer, I think, was very good for us. And yeah, to conclude, on overall, this was very successful. We are very happy with and we're happy that that the transition from laboratory scale to industry scale by CREA, that it was so smooth and in a very happy and friendly way. So we hope for more work like this. So thank you, and looking forward for your questions later in the question time.
Thank you very much, Linus, for your presentation. Our next presentation on timber elements will be presented by Andrea Klinge. She's a senior architect at ZRS Architekten. It is a Berlin-based practice of architects and engineers, where Andrea is leading the research department. ZRS is responsible for the design development for RE4 solutions for a fully reversible building, as well as for the refurbishment of existing buildings. Andrea will introduce the development of circular prefab elements from waste wood. The floor is yours.
Good morning, everybody. I'm very happy to be here and to present our work that we did during the course of the RE4 project. And thank you very much, Susanna, for the very kind introduction. I'm just... okay. Yeah, it's running now, sorry. Maybe just a few words about our practice. As Susanna explained, we're a firm of architects and engineers working very, very closely together. We do a lot of projects in Germany, but also abroad. And the main focus of our work is constructing with natural building materials. We use a lot of timber, but also earthen materials, and sometimes we have the opportunity to do experimental work, and we work with bamboo. What might be quite special and what helped a lot in the current project is that we have an own office lab where we can test materials. Right, so the reason why we work with timber is that we believe there are a lot of opportunities, first of all, in regards to circular construction. So it's a very suitable material for circular construction, as it is possible to construct dry and reversible connections, which is very important in order to make a building or an element reversible. It's a very light material, which helps again reversibility. It stores CO2. We have short construction times because full prefabrication is possible. In addition, it's a good thermal insulator, so you can achieve a high quality of thermal insulation through the material itself. And other issues that we are working on, in particular as architects, we always look into the comfort and the occupants' health, and low-tech construction. And again, timber is a very good material for these goals. So the challenge in the project that we were facing is that the reuse and recycling of timber is not really established. So we found out very quickly that there's no infrastructure in place. We had project partners on board who were responsible for sorting different waste streams, and the timber materials that we received were basically consisting of fibers that were often molded. So we weren't really able to construct any structural elements out of that kind of material, which made us aware of the situation, and we digged into this material sourcing a little bit more. And what we found out was due to cost and time constraints and the fact that virgin material is still very cheap, timber is not really recycled and reused very much. The main challenge with recycling and reusing timber is that you have to classify it according to the waste wood categories. There are 4 different categories plus PCB waste wood, but this is timber that you can't really bring back into the cycle. And what happens on site very often is that the construction manager doesn't want to take time to investigate the timber, so they classify by default the waste wood into category A4, and in that respect the timber can only be burned and can't be reused or recycled. Other challenges that we were facing is that very often modern timber constructions are based on metal fittings, and manufacturers are very much afraid that metal impurities could further down the line damage their machinery park. So again, this is one of the main barriers why there is no infrastructure in place to recycle and to reuse the timber. And one of our hypotheses is that what happens at the moment, we lose a lot of valuable material because there would be a lot of opportunities to take advantage of the dismantling of buildings where you have timber elements, because the quality of the timber, we believe, is often better if it's really historic timber, because it grew during different environmental conditions in comparison to timber now. And it had higher or better drying time. So we believe the quality of historic timber is actually very, very good. So this is really the situation that we are seeing in Berlin very often. This is a construction site where a building that you see in the rear was dismantled. It's a concrete construction at ground floor level, and it was constructed with a timber roof. And they didn't really take the time to dismantle it in a proper way. They just lifted the entire piece and put it to the adjacent empty construction site. So we approached the construction manager and asked for the material for the RE4 project, if we could use it. We did obviously all the testing that was required regarding the appliance of wood preservatives, which is quite important. And we managed to reuse this timber. But just to show you a few other sources for waste wood. So we have, when we look into historic constructions, we have a lot of wood in the system, in the structural system, as wooden beams, columns, or in the roof. Certain buildings are also constructed with timber facade elements, or we have timber in partition walls. There's a lot of construction work going on where timber is used as form work. This is what you can see on the right-hand picture. And this is just used for 2-3 months until the construction, in this case it's a bridge, is fully carried out, and then afterwards it gets burned again. So again, this is are really suitable sources where we can use timber for recycling and reuse. Just a few prerequisites that we're facing. I mentioned briefly wood preservatives is an issue. You have to classify the timber, and if, for instance, a wood preservative is applied that is not that you can't use nowadays, you have to react to this fact. But I will explain in a minute how this is possible. Then we need to make sure that the timber doesn't contain any other pollutants that might come from the previous use in a building. That happens from time to time as well. Wood destroying fungi or insects are obviously an issue. But again, there are laws in place how to deal with this. If you have, for instance, a timber column which has been infested, you just cut off the infested parts plus an additional defined length of timber in order to make sure that the timber that you can recycle or reuse is free of such negative impacts. Metal impurities, I mentioned before, is very not very challenging, but it's a barrier to timber recycling, because manufacturers are worried that metal impurities will damage their machinery park. What we did, which you can see on the second image from the left, we used a small metal detector, and we were investigating all the timber members that came in, and we were always identifying any nails or screws within the timber. And we believe we did it as a manual process, but we believe that it can be also industrialized. The other thing is, if you want to use timber for structural elements like beams, columns, or within facade elements supporting members, it has to have sufficient strength and also large enough cross sections. Just to dwell on again on this topic of wood preservatives, it's actually, for the time being, it's still a bit of a more complicated process, because you have to take samples and you have to send them to a certified lab. And what happens very often is that in larger buildings, for instance, you have a front building, you have a side wing, different substances could have been applied. So the investigation is quite time consuming. But during the research project, we came across another research project carried out by the Fraunhofer Institute, and they developed this hand tool that you can see in the picture, where they are able to identify appliance of harmful substances. And this is obviously very handy, because if you could use such a machine on site, you just run through and you can on site already separate treated timber from not treated timber. Just to show you a little bit the process that we were going through, because also we have to assess the quality of the material. So in this case, we took the material out of an historic attic in Berlin. We cut lamellas to a certain defined size that we defined as architects. We took metal fittings out. In this case, it was a bit more work. We investigated damages, cracks, but also branches, the dimension, the location, the depth, and so on, which is very important in order to assess the quality of the timber. And this is done then actually at industrial scale. It's done automatically. In this project, we had to do it manually, which is again a bit more time consuming, but normally this process takes place really at industrial scale. So for the different lamellas, you have a different sorting class, where you apply this to a certain standard. It's according to DIN 4074, and you have to assess branches, you have to assess annual rings, you have to assess cracks, and then you specify a specific sorting class. And on this basis, then you obviously you develop your structural elements like beams and columns. And again, these are assessed and according to standard again, and you specify the element itself according to a certain strength class, which again for the final construction is very important. For the design concept of the facade element, we came up with different indicators in order to set us ambitious goals. We specified the element as a non-load bearing facade element, because we believe that for circular construction, if you look at the entire building level, this is very important that you come up with a system where you can dismantle the facades quite easily, because the facade itself has a different lifespan in comparison to a structural system, for instance, which is much more durable and should stand up for much longer time. We also wanted to design a rear ventilated vapor open facade element. Rear ventilation is more expensive, but it has advantages in regards to durability, because the air layer protects the entire construction from moisture. And the vapor open aspect is very important when you want to design a building and you want to minimize mechanical ventilation. The other topics that we were looking into, fully reversibility through removable connections. As I explained earlier, in timber construction, it's very easy to achieve, because we can use screwed connections, and we can also use carpenter connections. These are dry connections plugged in, so you don't need any metal fitting for this. Another important aspect was material efficiency, because we want to be mindful with resources, and also material purity, because this is very important when it comes to dismantling further down the line. This was a lot of feedback we had from the industry. People who dismantle a building, if you use too many different materials, it's very, very difficult to separate these. Just to show you the example, the timber element in a little bit more detail, the green layers are actually layers that we were able to manufacture in during the course of the project, and the black ones are commercial products, because we didn't have any project partner who would manufacture these elements or components, but we believe that it's quite simple to do. So from the inside to the outside, we applied an earthen plaster, again on the basis of recycled aggregates that we developed during the course of the project. We achieved quite high recycling rates, up to 70%, which was quite successful. We then have a substrate for the plaster, a wood fiber board, which could also be manufactured on the basis of waste wood. We then need a wood fiber hardboard for stiffening purpose in order to provide structural integrity to the entire panel. Again, this is a product which can be also manufactured from waste wood, but we didn't have a partner on board. Then the main core of the facade panel consists of timber studs, which are the structural members within the non-load bearing element. And in this layer, we also apply the wood fiber insulation, which was actually a product manufactured by Chetma, again on the basis of waste wood. Then we need a DVD board, which is a weather-resistant board that protects the construction against any rain that comes through the weather shell. Apologies, that layer was also a commercial layer, so it should be black. But again, it could be manufactured on the basis of waste wood. And then we have battens and counter battens. In certain cases, it depends a bit on the orientation of the weather boards, if you need just battens or if you also need counter battens. Again, they are fully, they're manufactured from waste wood, and then we have the weatherboard itself. The advantage of timber construction is that you can place your window openings already inside the facade element. We haven't done this in this project, but in theory it's possible, and manufacturers are doing this already. And it's also, in timber construction, it's very easy to place your window. You have a lot of freedom as an architect with the facade design. Another topic that we were following is the opportunity for the cascading use of timber in order to be mindful with the material and to be material efficient. Our idea was that we maximize the outcome of the structural members that are incoming, and maybe the cut-offs we could use as weatherboards, and any other chips that occur during the manufacturing process could be used for the production of chipboards or hardboards, and any other fibers then could go into the development of wood fiber insulation or wood fiber boards that you need for the entire facade build-up. But the idea was also that, for instance, when you maintain a facade element, or you carry out maintenance, and you have to, for instance, the weather shell has been damaged, that you could use these timber components, and you chip them into chipboards, and you manufacture the next level of timber component out of it. So this is also something we carried out during the project. The incoming sections we have to cut, because historic timber used also core wood. This is something in modern construction you try to avoid core wood. Sometimes you have to cut out cracks. So for the timber studs of this facade element, we also developed components that are based on a framework in order to minimize the material usage. This shows a few different strategies that we applied in regards to the incoming sections. Another important topic for modern construction is the avoidance of wood preservatives. This is possible. We have a standard in Germany, and it specifies a certain type of construction, makes sure that that timber can dry out again, and then if you fulfill the requirements out of this standard, you don't have to apply wood preservatives, which for circular construction is obviously very, very important, because we try to avoid wood preservatives. This shows the design of the timber facade element. Again, in this case, we changed the orientation of the weatherboard. This had to do with the demo site. We wanted to make use out of the fact that we have exposed timber, and that we can assess whether the vertical boards differ significantly to the horizontally arranged boards. Another topic is screwed connections. We aim to have only one type of screw head, because we figured out that this is quite time consuming if you have to change your heads again all the time during the assembly. So this was also one goal that we tried to achieve. This shows you now the assembly process of the entire panel. The idea was that we would let this carry out by a subcontractor, but during the course of the project it became obvious that it's very important for us as a learning curve that we do the entire process ourselves. But as we are architects, we don't have access to to machinery park. So we did it really with a few hand tools. So on the first picture, you can see the assembly of the frame, the structural frame that you need as self-supporting structures with the studs and the horizontal members. We applied then a wood fiber board to one side in order to be able to apply the wood fiber insulation. In this case, we used not the mats manufactured by Chetmar due to the large amount of material that we would have required for the panel. So in that instance, we used a blow-in installation on the basis of wood chips. On the third image, you can see that we're closing the facade panel. And then once this is fully closed, you lift it up and you put all your sealing tapes in order to make sure that the facade element is airtight. We applied then another layer as a substrate for the earthen plaster. And then on the bottom image in the middle, you can see the application of the battens and the counter battens, and the application of the weatherboards. The weatherboards again are 100% recycled from a building in Berlin. These are old floorboards, and they had quite a nice appearance for our understanding. When it comes to the reversible connections between the element and the building, we also try to use very simple connectors. On the top, we used a commercial system provided by Halfen. So you have a steel plate that you connect to the building, to the facade element, but also to the building. And at the bottom, you use a steel angle, which is applied first, and then you lift the panel on top, and then you can actually fix the steel plate connector. Very, very simple and screwed connections. So the building element itself is fully dismantleable when a building reached the end of life. Also for the installation process, we looked into a very easy system of anchorage. You need a bit of support at the top, but these are simple screws that you can screw into your material, and you have these simple steel connectors that you can very easy and quickly apply. This is showing the installation of the facade element in Madrid. Alessandro was showing another image in his presentation already. It's attached to the second floor level. They could have used for the steel angle only pieces. It's quite a robust construction in that sense. It could have been really short steel angles, and not the entire length of the panel would have been supported. And this is just to show you a little bit also our assessment with regards to the outcomes of the assessment, what parts of timber you can use or reuse. This is actually a treated timber plank, so we had the obligation to cut off a certain amount of timber in order to obtain virgin material. So what we did was we cut out the solid elements that we needed, that are specified with UV, usable wood, 1 to 3 on the right-hand side, and on the left-hand side, these parts, due to the fact that the timber was treated, we can't reuse. We had to divert to a specific plant because it has been treated. But if you don't have treated waste wood, you could use everything that's laying on the ground. So this is showing you a little bit the outcome. So we have usable wood that is more than 50%, and then we have the offcuts, sawdust, where we believe you could also manufacture material out of it. But this is something that we have to prove outside of the project, because we couldn't investigate this as part of the RE4 project. Right, to conclude, in our elements that we manufactured, I showed you only the prefab timber element, but we were able to implement more than 95% of CDW timber, which we believe is quite a good achievement. Well, that's everything from my side for the time being. I give you my contact details, and I'm looking forward to any questions from your side. Thank you very much.
Thank you very much, Andrea. Our next presentation is about RE4 insulation panels and will be presented by Ilaria Ingrosso from CETMA. She's the head of Structural Health Monitoring Laboratory at CETMA. I would like to ask Ilaria to keep her presentation on time and as short as possible, as we are running out of time, but the floor is yours.
Sorry. Good morning. Thank you, Susanna, for your introduction. I will talk to you about our activities related to the production of insulating panels realized with the construction and demolition waste wood. Construction and demolition waste wood insulating panels are part of the project in terms of elements that can help in achieving the objectives 1, 2, 3, and 5 of the project, which are related to the maximization of recycled construction and demolition waste amount and value, the assessment of such materials properties, and the development of prefab elements, and then finally there was the demonstration in industrial environment. The different objectives will be discussed here on. Let's start with the first objective relating to the maximization of construction and demolition waste amount. Looking to the typical output fractions, construction and demolition waste insulating panels have been taught as products from the organic lightweight mixed material fraction, which is normally a landfill disposal element. Such fraction needs to be further selected in order to separate the different materials in it. In fact, it is normally composed of different materials such as plastics or wood. For insulating panels, wood has been chosen, even though attempts with the rigid plastic were also done. In this way, a construction and demolition waste fraction of material normally not used has been recycled in a new product. As far as it concerns the second objective of the project, the assessment of the construction and demolition waste derived materials, wood for the realization of insulating panel was tested in terms of physical performances. The analyzed material was recovered by an handmade selection in recycling plants from the lightweight fraction in order to have the less contaminants as possible. First of all, the assessment was conducted in terms of geographical provenance. CETMA request was wood in scraps with a dimension smaller than 10 centimeters in length, and coming from two different regions, which were Southern Europe and Northern Europe. So two different batches of lightweight materials have been analyzed. In the figures, you can see samples of materials coming from the different regions. As it is possible to see, the scraps were physically different depending on the provenance. Scraps coming from South Europe were bigger but more homogeneous in dimensions than the material coming from North Europe. Moreover, wood from South Europe arrived as pieces of dimensions in the range between 100 and 200 millimeters. For this reason, it was necessary a further grinding process in order to reduce the material in fibers. A grinder with a sieve with a circular mesh of 20 millimeters was used, and as far as it is concerned wood from Northern Europe, it was delivered already in chips and fiber shapes, so no further grinding was necessary, but only a sewing step. In this table, the methods used for the geometrical and physical characterization of construction and demolition waste lightweight fraction are summarized. When no standards were available, technical procedures reported by wood panel producers were used. Wood fraction has been characterized to define particle sizes. Two different characterizations have been carried out. The first one here showed, according to the methodology described in European Standard 933 Part 1, has been a one-dimensional sorting in order to determine the ratio of powder or near powder size particle on the total amount of material. Moreover, first data on size distribution have been acquired. For each batch of wood fraction, 8-liter volumes have been tuned with this method. The second characterization method is reported in the picture. A manual sorting of the particle has been carried out, separating particles as a function of the length. This work was aimed to define the typology of particles present in the wood fraction, for instance, chips, fibers, wood wool, and their range of length. 4 different classes of length have been used for the characterization: 0 to 2, 2 to 4, 4 to 6, and 6 to 8 centimeters. The difference in the graded classes is due to the choice of using a 20 mm mesh of grinding 2 for the Southern Europe material. In the table here shown are reported the calculated average values of density and moisture content on 5 different samples for each source of material. The density of wood fraction is obtained by the ratio between the mass of wood particles and their apparent volume at a predetermined moisture content value. The moisture content in wood fraction was calculated as the ratio between the mass of the water in wood fraction under examination and the same anhydrous wood fraction. In order to obtain the anhydrous wood fraction, the execution method has been carried out until the mass stabilization. The high difference in terms of density is dependent on the difference in moisture content of the two wood fractions, as confirmed by the anhydrous materials. Let's talk about the development of technological process for the manufacturing of construction and demolition waste wood insulating panels that was realized through following the third objective of the project. Such part of the work was conducted through a process of molding under pressure. In the following slides, photos representing the different steps necessary for the process are reported. So the first step was the sewing of the material. In order to eliminate those pieces of wood that were bigger than the chosen dimension for the panels and with such a shape that could not be interviewed, a sewing step was realized, and generally the wood was sewed in a 4 mm mesh sew. Then the second step was the soaking of the material, reported in the picture in the upper part of this slide, and the selected material was soaked in water. Then there was the filling of the mold, as shown in the photos in the lower side of the slide. Soaked material was introduced in the mold after being roughly dried by the water. Depending on the quantity of material to be introduced, preliminary pressing steps were assessed in order to compact the materials. Then the material in the mold was kept under pressure and in temperature in an hydraulic press. The wood insulating panels production process was defined through 4 different parameters: the temperature, the time of molding process under pressure, the mass of drain, construction and demolition waste wood material, and the construction and demolition waste wood grading class and geographical origin. After this step, a cooling to room temperature step was realized, where the mold was removed from the press steaming temperature and then cooled down till room temperature. Finally, there was the demolding of the panel, where the panel was removed from the mold. The process optimization was related to the bulk densities of the panels in order to achieve the desired insulating performances. Physical and mechanical properties of produced wood panel were also investigated. In fact, in this slide you can see for the obtained panels divided by class of density, the compression stress at 10% of strain. When the insulating panel application requires fire resistant properties, wood mineralization process can be realized in order to substitute part of the organic matter of wood fibers with mineral matter. In our work, the selected mineral was magnesium oxide, and different lab trials were conducted in order to develop the process. Mineralization process was carried out before soaking the wood in water for the insulation panel production process. In details, wood was kept in autoclave under vacuum to obtain the degradation of wood fibers. Then was realized the injection of mineral suspension in autoclave. The autoclave was pressurized in order to force the mineral solution to soak the wood fibers. And then the mineral suspension was removed and the autoclave depressurized. In figures in the red rectangle on the left show representative wood fibers soaked in water before and after the mineralization treatment. The observed treated fibers are covered by mineral parts. On the right, the thermographs detected by Mettler Toledo equipment of 4 different samples are reported. An interesting results can be observed at about 500 Celsius degrees, where no residuals are observed for wood fiber untreated, while a residual of approximately 10% of mass with respect to the initial treated wood mass is observed. The last objective followed with the panel's development was the feasibility in industrial environment. In order to develop a pilot production line, a new mold, which could be opened and stacked, was designed and realized. Then the number of panels necessary for the realization of the demo building was realized. And finally, the panels were shipped to the demo building sites and installed. I thank you for your attention, and I will be very happy to answer to your question if there will be any.
Thank you very much, Ilaria. Our last presentation for this webinar will be presented by Sandro Blasi, who is a material engineer and project manager at Vortex Hydra. He's in charge of following the tasks Vortex Hydra is involved with within the RE4 project. He will now present the extruded concrete tiles. The floor is yours.
Thank you, Susanna, for your introduction. Thank you to the crowd for their patience. My presentation deals with the extruded concrete tiles developed within the RE4 project, and I will spend a few words just to introduce the company I work for, Vortex Hydra. Then we will go through the overall goals Vortex Hydra has been charged with, a list of the main obtained results, and a few concluding words. Vortex Hydra has been established, dated back in 1967, and with a wealth of experience of 52 years, he has gained a leader position as a producer and manufacturer of automatic concrete roof tile plants. We have the largest customer base with more than 500 clients spread all over the world. And Vortex Hydra owns a few patents in that field. And in the development, design and manufacturing of the automatic plants and equipment for concrete roof tile. We are supported by a quality management system and an environmental management system. We do also have a second division which deals with hydroelectric power plants, totally different beast, but it is just to show the sensibility of the company for renewable energy. Vortex Hydra has been selected as an industrial partner within the consortium of RE4 Project, and we have been tasked with the following goals. First of all, goal 1, the maximization of the use of CDW-derived aggregates in lieu of virgin aggregates for the manufacturing of extruded concrete tiles. Goals 2 was the investigation of potentially required modification or upgrade to standard equipment for the industrial production scale. And goal number 3, very practical, was the production of 60 square meters of extruded tiles to be delivered to Madrid demo site, erected and handled by Acciona, another partner of the consortium, plus another 15 square meters to be delivered to the Matrix station in Benevento, South Italy, handled by another partner of the consortium, Stress. At the beginning of the project at Vortex, we have carried out a preliminary investigation about the possibility of using CDW-derived aggregate for manufacturing extruded roof tiles, because as I told earlier, the manufacturing of automatic plants for roof tiles, extruded roof tiles, represents the core business of Vortex Hydra. We have carried out a series of trials, and because of the strict EU standards in force, both in terms of the requirements for flexural strengths and for water tightness, which are described in the standard EN 490 and 491, we have been forced to limit the replacement rate of virgin aggregates with CDW-derived aggregate to a 50%, which represented a lower limiting threshold within the project. In the picture on the left side, you can see the equipment to test the water tightness of the extruded tile. And on the left, we have a 3-point bending machine to test the flexural strengths of the extruded tile, roof tile. And basically, that percentage of replacement, which was set at 50%, was due to the fact that for the extrusion process, when we have to reach very high standards in terms of flexural strength and of water tightness, we have to deal with a very well distributed Fuller curve, which is a representation of the grading of the ideal distribution of the aggregate size in order to get the most suitable density and the highest flexural strengths. Then we have focused our attention on extruded elements for facade cladding, and we have addressed our attention to a product we were familiar with, which is an extruded tile which represents the base element of a patented cladding system for walls. And basically it is an extruded tile called stone, which has a dimension of 600 millimeter as far as length is concerned, with a width of 100 millimeters and a thickness of 10 millimeters. The extruded tile, the stone, is shaped in a way it can be easily hooked to a mounting rail system, which is represented by a series of metallic rails, vertical and horizontal, which are fixed directly to the substrate wall. The fixed system, thanks to a series of spacer with variable lengths, is ideal to realize ventilated or insulated facade, and it is possible inserting within the gap between the substrate wall and the facade finishing element, insulating element. It is possible to get transmittance values which are responding to the standard in force in Europe. As goal maximization, as a goal, we had the maximization of the use of CDW derived aggregates in lieu of virgin sand. We used a mixed design that we were familiar with a water cement ratio of 0.25 and an aggregate cement ratio of 3. As an hydraulic binder, we have used Portland cement type 2, 32.5. And we have been able to reach an 85% replacement rate, which is very encouraging. The last 50% was made of fine sand because of the rough granulometry. It was not possible to process the full replacement material, where CDW derived aggregates were the substitution element for virgin sand. It was very interesting, the fact that during the tests we have carried out, and also using the experience developed along the years of working in this field, it was really interesting to see that any upgrade or specific modification was required by the equipment, by the standard equipment to process the material with CDW aggregates. So basically, in an industrial scaled up plant, we can have a batching plant, usually working with a planetary mixer, because it's the one which grants the better homogeneity and better mixing. Then the fresh concrete is conveyed to the extruder, where the extrusion takes place. Fresh concrete is put inside an hopper, and on the other side of the extruder, aluminum pallets feed the extruder, and then the fresh concrete, shaped in its final shape, is conveyed via a system of conveyor belts inside a curing chamber. It is basically a single atmosphere environment where the parameter of temperature and relative humidity are strictly controlled. Temperature can be increased by supplying it from the outside in a controlled manner if you want to speed up the cement hydration reaction. Once the extruded tiles have reached the desired degree of hardness, they are conveyed to a depaleter, which is basically a machine which separates the aluminium pallet from the extruded product. Then the aluminum pallets are recirculated back in a closed loop to the extrusion head to process more fresh concrete, while the extruded tiles are packed, strapped, palletized, and ready to be stored in the storage area. Seeing that, we have started the production of the extruded elements that had to be delivered to the demo sites in Spain and in South Italy. In the picture, in these slides, you can see the extrusion head with fresh material. Then we have at the exit of the extruder longitudinal blade, which splits the extruded element into symmetrical parts, and a vertical blade which cuts the extruded tiles to the desired length. Elements are then cured, and on the bottom picture on your right side, you can see an example of extruded stone hooked on the support frame. I have also inserted in this slide a very short video. I hope you can see it. Showing the action both of the longitudinal cutting blade and of the vertical cutting blade. Elements produced have been then delivered to the demo sites in Benevento. On the left side, a picture collected during the last January assembly we have had, the metric station with a wall equipped with the extruded stone manufactured at Vortex. And on the right side, an erection phase of the demo building in Spain, where prefabricated building manufactured with elements produced within the RE4 project will be put in comparison with a standard building. So here you can see that extruded elements are ready for field test, because at metric station the wall will be equipped with a series of probes and sensor in order to check the thermal performance of the wall, and also seismic tests will be performed on site. And it will be also interesting to see the time for dismantling once the project will come to its very final stage. Resuming some concluding words. First result, the maximization of the use of CDW derived aggregates in lieu of virgin aggregate was achieved with a very, very interesting percentage of 85%. That has been achieved for extruded tiles to be used for facade elements. This percentage is much higher than the one reached when we had to deal with concrete roof tiles, because for concrete extruded elements for facade wall, there isn't actually AN standard which prescribe lower thresholds in terms of flexural resistance. Second result, very important, good news for those who already have a plant on site. is that there isn't any need of any upgrade on standard equipment to process CDW-derived aggregates. And as told before, the most tricky aspect was that concrete roof tiles imposed a quite low replacement rate, which was anyway within the minimum target that was one of the main goal within the project at the beginning in 2016. For me, it's all. I'm looking forward to receive any question or curiosity which might meanwhile arisen. Thank you, everybody.
Thank you very much, Sandro, for your presentation, and thank you all presenters. As we have finished all the presentations, it's time for questions. We don't want to keep you too long. We have received many interesting questions, but since we are running out of time, we will ask one question and answer the rest of them privately. The question is from Linus from RISE, and the question is, what is the main benefit of the RE4 non-structural panel compared with the RE4 structural panel?
Okay, thank you, Serena, for that question. To answer quite rapidly, both are very good because they are based on high levels of construction demolition waste in the concrete. But the extra benefit of the non-structural panel is that the carbon fiber reinforcement, it's in itself, it is lighter than the steel reinforcement. And this, together with that, it's now also possible to make the panel much thinner. So we make it half the thickness of the ordinary outer layer. That also reduce the weight. So in total, reducing the weight with maybe 20% of the full sandwich panel. And also, of course, in dimension, you can transport and store these a little bit tighter. Another benefit with carbon textile reinforcement is that it doesn't corrode like steel reinforcement can do. So yeah, every solution has its pros and cons, but these are some of the benefits of it. So I would say making it more corrosion resistant and reducing the weight would be the major. And it's interesting to see that we managed to do this high performance concrete using this textile reinforcement also in these panels.
Thank you very much for your answer. Thank you very much to all panelists and for the questions by the audience. As I said, we will answer other questions in private, or you can contact the panelists directly. It was a great opportunity to hear from all the partners of the project. Special thanks belong to ACR Plus for technical support of the webinar and Phoenix team for organization. We would like to invite you to the next webinar, webinar number 3, with the topic how to build a fully recycled house, which will be on the 22nd of January 2020. You will hear more details about the demo sites in Spain, UK, Italy, and replicability in Taiwan. You can register for free on the RE4 website. We would also like to invite you to a workshop in January in Madrid, where you will be able to visit the Spanish demo site and see the fully recycled house in real life. Thank you again, and see you on the next webinar.
Thank you to everyone. The webinar is ended. You will all receive a link with the recording of the webinar, so you will be able to see again the presentations and to listen again the webinar if you need, and you will be able also to promote it and send it to somebody that can be interested in it. Thank you to everyone and have a great day.